This is emmetropization, signals components for growth for V551. For the eye to emmetropize naturally, there's different components within the image processing that need to take place for the eye to emmetropize normally. Here's 4 examples of those things. There are other ones out there. The first and the biggest one is the sign of defocus, and that's where the image is placed relative to the retina. Second, the time of exposure, what we call temporal processing, is important. It's also important to know how it responds to dual or competing focus within the eye. And finally, how does light levels affect our emmetropization process? We've discussed sign of defocus before, but to simply put, myopic defocus, or if we place the image in front of the retina using plus lenses by giving it too much power, the eye will slow or shorten its growth. So this is a stop signal or a shortened eye signal. Conversely, if we have a hyperopic signal where we place a minus lens to decrease the power of the eye, this puts the focal position behind the retina. When the eye's focal position is behind the retina, the eye will grow longer to find that focal position and optimize light, but the ultimate result is more myopia or a longer eye. You might ask yourself, a few weeks ago I looked through a minus lens, is my myopia going to increase because I just looked through this minus lens? The answer is obviously no, and that's because of temporal processing. You can think of temporal processing as the amount of time for some sort of biological event to happen. An example of that is, how long do you have to look at something to detect it? When we talk about emmetropization in temporal processing, we're talking about how long does a defocus signal need to be there to cause a change in axial length. And that can be done in different animal models. Here's an example of one experiment where they took a hyperopic signal, so they put the image behind the retina in one group of animals. In part of the group, they took the lenses off every once in a while. To be exact, they took off the lenses about an hour a day, 15-minute intervals every 4 hours or so, for an hour total. In the other group, they wore the minus lenses the whole time. What happened? The eyes that had the lenses on full time became more myopic and longer. But the eyes who had even just a brief 1 hour a day period of clear vision had no difference from the control group. So what does this tell us? First of all, that we need long periods of time of constant viewing of a target. About an hour of focused vision stops elongation, so any constant signal that's there for weeks and months is a potential for changing our emmetropization or increasing myopia or hyperopia. Short periods of time, though, of clear vision clear that up and prevent that. Now, how does the eye respond to what we call dual focus or competitive focus? Well, we can do that with experiments to actually change the focal position. We can do that with either Fresnel lenses, bifocal lenses, or multifocal lenses. And we can put part of the image focused in a different location than the other. One example might be to put the light focused in front of the retina in one part and behind the retina in the other part. And we can then see how the eye responds as far as its growth. We actually do this in humans as well through actual bifocal light contact lenses where we put the images at different parts to use for myopia control. So this allows clinicians and researchers to partially focus in different locations. As another example of this, we could take 50% of light and focus it in front of the retina. And we could take the other 50% of light and focus it on the retina. So how does the eye respond to that as far as its growth goes? Well, here's an example in animals. When we have a 50% myopic defocus, so the image is in front of the retina, and 50% of it is on the retina, the eye stops growing. So the focal position is actually strong for shortening the eye or stopping growth. Conversely, though, if we look at the hyperopic signal where the image is placed 50% behind the retina and 50% on the retina, 50% of vision in clear focused on the retina was enough to stop any growth of the axial length. So our control group and our test group, when they have 50% hyperopically defocused, controls and stops myopia progression. Light levels also might play a role in how our eyes respond to defocus. Here's an example where they did form deprivation at different light levels. In one group, they had 500 lux of light levels, so the animal was reared at 500 lux, and in the other group, the animal was reared at 15,000 lux. Even though both animals experience form deprivation myopia, what happens is the group that has the higher light levels has less myopia. The actual axial length actually decreases. And this has been found in a number of animal models, both with foam deprivation as well as defocus systems. High light levels seems to stop axial elongation or slow it. How does that apply for us in humans, though? Well, first of all, our light levels indoors versus outdoors are radically different. If you look at the indoor light levels, we're at about 500 lux on average in our normal environments. When we go outside on a sunny day, there is many orders of magnitude brighter outside in the sun than it is in our offices, in our playrooms, and all these other things. Even on a cloudy, overcast day, it's still twice as much light outside as in the brightest office room. Well, we start to see these things, then how it affects actually myopia progression. Here's a series of studies looking at the change in myopia progression or axial elongation based upon the seasons. One of those is an IU graduate, an IU faculty member. What we see is people have the longest or the most growth during the minimum daylight periods of the winter times. Conversely, during the summertime, when there's high light levels, there's less myopia progression. So this suggests possibly light levels are a contributing factor. Now, a smart person might say, but it could be accommodation and near work because they're in school versus out of school. And we'll discuss those myopia theories of progression and development later in future lectures. Regardless of that, though, there have been a number of studies who've looked at the effects of outdoor time versus indoor time on its progression of myopia. And the majority of them find that the more time you spend outside, the less your myopia progresses. Thank you.